yeah, the preeminent feature of C++, the one feature of C++ that makes this language stand out from any other is deterministic destruction. You know that when the name of an object falls out of scope, then the thing that it's attached to gets destroyed and all its resources are released, including the memory that it's occupying, or rather the address space that it's occupying. Now, for that to be the case, that means you need to manage the memory very closely. And there are four classes of storage. Okay, so there's static storage, automatic storage, thread local storage, and then there's dynamic storage. So automatic storage is what happens on the heap. So you open a function, so you go into a function, you open a pair of curly braces, you declare a name and define an object, and when that name falls out of scope, the object that it's bound to is destroyed. So that's really simple. We don't need to think about that at all. Then we have static storage. Now, this is these objects are initialized at startup. So you start your program, you run all your static storage, you initialize all your static objects, and then you call main. This comes with its own set of problems because you might have there might be circular dependencies going on that you can't resolve because you haven't hit main yet. And then you've got thread local storage, and this is like static storage, but it's per thread. So when a thread is spun up, then it will do all its thread local static storage. So the tricky one is when you want an object whose life cycle is neither that of a function nor that of the entirety of the program. Yeah. So it kind of works, in between. You want something to persist for a while, but not for the entirety of the program. But you want it to persist longer than the function in which you created. And that's when you have to use dynamic allocation. So static, dynamic, automatic, thread local. Those are your four storage classes. Now, dynamic allocation, unfortunately, because it's not automatic, because it's something that you schedule, means that you have to look after when things are created and when they're destroyed. You also have to look after how they're created and destroyed. Well, you don't have to look after that, but if you don't, it's going to cost you, because by default, when you say, all right, I just want to allocate this thing on the heap, and the heap goes, okay, great, how many bytes do you want? And you say, I want 64. They go, there you are, there's 64 bytes. The thing is, allocating and deallocating, allocating and freeing, can really fragment your address space. It can make lots of, you might have like dozens and dozens of tiny little allocations, and then a few, and you get this thing called fragmentation where you'll allocate a lot of things, but you'll deallocate a few of them, and you might have only used half of your address space, but it's completely swamped by these little pockmarks, these little holes in your address space, where you can't make larger allocations. So what you have to, there needs to be this whole set of strategies for ensuring that you minimize the amount of fragmentation. And usually you'll do these things called slab allocators or arena allocators. And that's where you'll say, right, I want you to put all the 64 byte allocations in here, or I want to put all the 512K allocations in here. And the advantage of that is that you don't get unwanted holes, because any hole will be immediately filled by another 64 or 512K allocation. The other thing that you might know about that heap allocation won't know about is how long you're going to be allocating something for. Now, if you know that you're only going to be allocating a thing for a particular, one tick in the game, for example, or for, it's going to be allocated, it's going to be deallocated by the time this function is exited, then you can say, all right, well, look, all of these things that we know are going to be destroyed by the time this frame exits, we can create a little bit of memory for there, a small subheap for that, because we know it's going to be a small number, and we know it's going to be empty by the time we get out of this frame, and then we can start, and then we can start again. So those sorts of things will improve the improve the performance of your memory allocation. The trouble with your default allocation is the worst case scenario. You're saying, I know, that allocator says, I don't know how big these things are going to be. I don't know how long you're going to want them. So, here you are. Now, this was much more of a problem in the sort of 32-bit days, because in the 32-bit days, when I was writing a game on Windows, I had 2 gigabytes of address space, or 3 gigabytes if I could persuade the user to muck about a bit. But with 2 gigabytes of address space, modern games, you run out of that quite quickly. You find yourself trying to, shoehorn things in the right place to, trying to just just to administrate all of this memory. It's an enormous problem, because the other thing that you've got to do, besides administrate all this, is keep track of it all. You've got to know when you're filling up your amount of space, and when what your largest available allocation is. You've got to know these things so that you can control what's going on. You can't control what you can't measure. So writing all those feedback systems that say, hey, you've got a lot of allocations of 64 bytes going on here. Maybe they could have their own arena or something like that. These are all things that you need to take into account. It's a big topic. It really is a big topic. And I think that it doesn't seem to be something that's taught in universities or anything like that. I go to a lot of universities and say, hello, my name's Guy, come and write games. And I usually give a lecture, and I give a lecture about low-level stuff like memory management, and it's a closed book to everyone, but it's absolutely critical. You've got to manage your memory, you've got to manage your resources, otherwise your game will fall to the ground. It will crash and burn. There are plenty of titles out there that have suffered enormously from not being able to manage their memory appropriately.
Do you think that games why in the other parts of software engineering we don't do that so meticulously?
You don't need to. So look, I've got a PlayStation 5, okay? Actually, let's go back a bit. I've got a PlayStation 2. I've got 32 megabytes of RAM. I can't add more RAM. I can't do any of that. That option is not open to me. When you're working on a domestically specified device, that's what you have. Embedded programming, same sort of situation. An embedded, when in embedded programming, you have a few K, and that's it. You can't say,
But today, now, all of our machines, both on the, let's say, gaming PCs, have more memory, as well as servers that, let's say, run web servers or whatever. Why is that? Why is that our gaming PCs with 64 gigabytes of RAM? Maybe let me ask another question.
Yeah.
What is the default memory that you're thinking about now when you're making a big PC game? If it's 64, then you pretty much have probably a lot of space to not care about the memory.
Well, unfortunately, no.
Okay.
This is the this is the big problem. The thing is, you've got 64 gigabytes of RAM in your machine, but you have a whole bunch of processes running. They're all taking up a bit of memory address space. The thing is, I keep saying address space and not memory, because address space is each process that's running has its own address space, and if all your processes had the full amount of address space available to them as 64-bit processes, then they would quickly completely exhaust the RAM in your machine, because a 64-bit address space is exabytes in size, and you've only got gigabytes of RAM in your machine. What happens is that you use up some of your address space. All of these processes, they'll use up some of their address space, and that portion of the address space that's in use is what is backed in RAM. Okay. Now, the more RAM you put in, the more processes you can run, the more address space they'll take up. But the thing is, sooner or later, you're going to run out of RAM. You'll have so many processes doing so many things that you'll run out of RAM. Even if you're running a game, you might end up, your process might grow and grow and grow, and then your address space will fill up. Well, no, your address space won't fill up, but your RAM your address space will exceed the amount of RAM available for backing. Now, what happens then is it'll swap it out to disk. It'll say, all right, you want this page, you can swap out to disk. You don't want that happening. That slows your game down. A swap takes time. It is a non-trivial amount of time. It is a measurable, observable amount of time when a swap happens. So you want to keep your address space utilization optimal. You want to keep it as unfragmented as possible so that you don't end up swapping. Because you say you've got a 64 gigabyte machine. There are people still playing Total War on laptops with 4 gigabytes of RAM. You know,
Okay.
you can't just say, "Hey, all our games, they've got 64 gig, that's fine." If they haven't got 64 gig, honestly, get a life, you loser. You can't say that
Yeah,
because
yeah.
you minimize your addressable market. You know,
Okay.
64 gig is a lot of RAM, but
But
you know,
you
your
have
market
to like have a conception of the, let's say, minimum memory that you're.
specification. Yeah, I don't know what the min spec for the last Total War game was. I think it was 8 gig. I think we're going to be at 8 gig for a while. It's, you know, you've got the Steam survey will tell you what people have.
Yeah.
You know, it's, you can decide, all right, I'm going to insist on 32 gig of RAM, but that's going to cost you customers. You know, if customers say, oh, I don't have 32 gig of RAM, I can't play this game. I had a machine. So I bought a new machine in November. I bought a machine at the end of last year. And it's my first new machine since 2011. Okay. Now, I've upgraded the graphics card, but the motherboard and processor is still the motherboard and processor I was using in 2011. And I was able to run games fine. You know, all the games I wanted to play, I was able to play. Which, that's worth bearing in mind. You know, 12 years.
Yeah.
You know, no one's releasing games for the PlayStation 3 anymore, and that was prevalent in 2011. Anyway, so 12 years, I got an upgrade. Now, one of the games, and one of the things that drove this was that I wanted to play Deathloop. I don't know if you've come across Deathloop.
Yeah.
Fantastic game. Really, really interesting, clever game. I've enjoyed it very much. I really have. And Arcane Leon are to be congratulated on, you know, really good production there. I tried playing it on my 12-year-old machine, wouldn't have it. It just fell over, and it kept on crashing and giving me dialog boxes saying, "Oh, exception here." And I sent my sent specs to us. I contacted technical support at Arcane, and they said, "Oh well, yeah, your machine's not up to the job." And there was this, and it was the first time that I'd had a game that I couldn't play for which the machine wasn't up to the job. And so I thought, all right, well, I'm going to have to upgrade, aren't I? And so I did upgrade, and I went all in. So I thought, well, I've got a new job coming up. I'm going to be fully remote. I may as well absolutely go for it. So I've got 64 gigabytes of RAM. I've got a 3090 NVIDIA GPU part because I couldn't be bothered with the 40 series. I've got monitors up the wazoo. You know, I absolutely went for it, and it's a great, you know, I've got a great piece of kit. But it cost me, you know, over $2,000.
Yeah.
A console doesn't cost you $2,000. A console costs you, you know, a few £100. And you know, if you're going to buy a PC for a few £100 to play games on, you know, it's all very well developers having massively specified machines at their desks, but those aren't the machines that their customers will be running on. That's why you have to worry about memory. You have to worry about optimizing your resource utilization at all times.
Yeah. So can you let's say throw in some of the examples? You mentioned the linear allocators to have, not to fragment your memory, but to allocate some chunks of memory of the same size alongside each other. What are the other techniques for the memory?
Okay, so for example, you could have what I call a stack allocator. So this is an allocator that works like a stack in that you allocate and deallocate in reverse order. Sorry, you deallocate in reverse order of allocation. So it works like a stack, but you can't be certain that other allocations won't be happening in between. So for example, if you have a user interface screen and you say, right, okay, you're in the front end of a game and you say, right, I want to tweak the graphics, I want to tweak the graphics options, I want to tweak the shader options. So you've got 3 screens coming up in front of you. Now, whilst you're making changes on those screens, you're obviously creating objects which are going to feed back into how the game is operating. The objects that will describe the game you behave like this. But the screens themselves, you know that you're going to go back through the screens. They're going to be created in order of navigation through the screens and destroyed in reverse order. So you can say, all right, well, look, let's allocate everything and then deallocate everything in reverse order. And let's have a special area just for the UI components.
Okay.
So that means that you don't get fragmentation, because otherwise you'd be allocating those things and then you get your little objects that you're allocating for much longer, and then you'd lose all your then you lose all your user interface components
Okay.
allocations, and you've got these little bits scattered around that you're creating in the way. This is the typical problem that you get with allocations. You allocate objects in order to allocate other objects, and then you deallocate loads of the objects that you created, but the one that was meant to last a long time ends up sort of stuck in the middle of nowhere.
Okay. So you're trying to match the life cycle of the objects to the allocation and have it closely connected to allocate and deallocate at the same time. The proper, let's say, life cycles. Okay.
Yeah.